Hello, everyone. This is Borrell from BSC, and I will be chairing this session. It's the first session of the first joint CoE technical workshop, and is devoted to load balancing. Okay, we'll have speakers from 3 centers of excellence that are organizing the workshop. That is Hidalgo, Cheese, and Extragat, and then additional contributions from POP and from EPIC projects. Let me put full screen. Okay, first of all, I will start with a little bit of motivation. The problem with load imbalance is associated to idle resources at synchronization points, right? Load balance does not mean same computational or same workload per parallel process in a parallel execution, but same computing time or same time between synchronization points. That's what we want to achieve in order to avoid the waste of resources of that stay idle on the synchronization points when process arrives before to the process that arrives before to the synchronization points stay idle until the last one arrives, right? The synchronization points are generated by data or computational dependencies on the shared memory or on the distributed memory context, and are not necessarily between all the parallel processes, but can be between 2 processes as well. Okay, any dependency and a communication or a barrier will produce a synchronization, collective or partial, and this can produce idle resources if the process don't arrive at the same time. And as you see here in this trace, this is from an execution in Alia. The problem with the load balancing can be catastrophic compared to the communication overhead. Okay, here in this image you see the blue is computation, and the orange and yellow are communications. And this orange and yellow communications should take the same time than the other communications within the solver, the linear solver. This part here is the linear solver, right? But as one of the parallel processes, the computing phase that comes before these communications is not well balanced, okay, all the processes will be waiting until the last one arrives. So imbalance, it's critical, or balancing, it's a critical issue to get. Otherwise, the waste of resources can be really catastrophic. Some complexities that we have when we want or some threats for the balance, okay? Well, if we look at it from the application data and algorithms, the most problematic thing is the heterogeneity, okay? This heterogeneity can be in the data. For instance, in a numerical simulation, we can have heterogeneous meshes with different types of elements, and it's different to figure out or to model the cost of each element, of each particular element. We can also have particular algorithmic setups. For instance, the boundary layer model that only will affect one zone of the domain. We can also have algorithms with indeterminate cost. For instance, a search algorithm, or in some cases, the physics produce also dynamic workloads. Okay, when we have adaptive refinement, when we have particles in our simulation, when we have interface tracking problems, all these the phenomena, the simulation or the computational load gets imbalanced or changes through the simulation, right? So those are complexities of the problem itself, and also from the hardware's point of view, heterogeneity in the hardware also complicates the balance when we want to use simultaneously CPUs and GPUs, for instance. And also performance variability. We can have dynamic frequency scaling of the CPUs. We can have operational failures that are not expected, etc. There are also some components like the network or the I/O system that are subject to noise. So all these components make the balancing problem really complicated. If we go to different solutions, and we will see some of them here today. Okay, there are many classifications of possible load balancing strategies. I like to classify them in 2 types: the ones that improve the distribution, so improve the balancing, and the other ones that when the balancing or when the idle resources coming from an unbalanced problem appear, they try to use it for computation. They try to react at that point and use that idle resources to do some computations, right? It's not the same, okay? The first one would be, for instance, redistributing the mesh if you detect some imbalance in your simulation, or redistributing the computational resources. And the second one will be a strategy of migrating tasks at the synchronization points when there are idle resources, okay? Or reallocating computational resources. We'll see one in our task today. We'll see one in this case. We'll see one strategy based on migrating tasks, another one based on migrating resources, which that is not exactly the same. Okay, so we have different type of strategies. The best strategy will depend on the problem, and in fact, those are complementary. So if we have if you have an imbalance produced by something, some aspect that will be persistent, it will be better to try to correct the distribution. Otherwise, these runtime mechanisms that help you to mitigate the effects of the imbalance will be solving the same problem every time, right? So if we have some kind of imbalance that is persistent, it's better to correct the partition. Otherwise, if it's something spontaneous due to hardware issues or whatever, then the best solution, or the real solution would be something, some runtime mechanism that acts instantaneously. Okay, so those are more or less the ideas, and it's very interesting today that we will see different strategies, and probably that all of them can be, or most of them can be combined. Okay, so to conclude the introduction, the agenda for today, we have 4 talks. The first one is focused in Alia, and the speaker will be Marta Garcia from POP, and also myself. Then we will have a talk from Gabriela Staffelberg from Surfax, related with ABBP, and the work is related with the projects Acceleract and EPIC. And then 2 more talks from Michael Bader from the Technical University of Munich, and from Robert Elsasser from University of Salzburg, okay, that come from the CHIS and Hidalgo project.